Let's take a look at a few examples where we need to calculate the equivalent resistance. In other words, if we're given a set of resistors and we want to take them all out of the circuit and replace them with just a single resistor, what resistance should we choose? It looks like in the first example, we have one resistor in parallel with two resistors. Let's combine these two resistors in series first. We still have 6 ohms up here, and 2 plus 4 equals 6. So we have a 6 ohm branch down here as well. 6 ohms in parallel with 6 ohms is 3 ohms. In general, if you have two resistors in parallel and they have the same resistance, you can find the equivalent resistance by just dividing it by 2. In this particular example, we started off with two 6 ohm resistors. In parallel, we wind up with 3 ohms because 6 divided by 2 equals 3. If these two resistors had instead been, say, 20 ohms, then combining two 20 ohm resistors in parallel would give us a single 10 ohm resistor. Sometimes when combining resistors in parallel, it's a bit tricky to take the reciprocal, add, and then take the reciprocal again. So let me show you another way to do it in your head. Imagine that we have two resistors, R1 and R2, in parallel, and we want to know what the equivalent resistance is. We already know the formula for equivalent resistance. The reciprocals just need to add like this, but this formula is a bit tricky to apply in practice. It's easy to get lost with all these divisions. So let's take every term in this equation and multiply it times R1, R2. And this brings us to a formula that's worth remembering. When you have just two resistors in parallel and you want to combine them, rather than going through the business of taking reciprocals, you can just remember the following. Multiply in the numerator, add in the denominator. Multiply in the numerator, add in the denominator. So in the example here that we've just worked, we had two 6 ohm resistors. The trick is divide by 2. But let's say that instead we had one resistor that's 3 ohms and another resistor that's 9 ohms. What would be the equivalent resistance? Multiply in the numerator, 9 times 3 is 27. Add in the denominator, 9 plus 3 is 12. The equivalent resistance would be 27 divided by 12. By the way, that trick only works if you have two resistors. If you have 3 resistors in parallel, then that trick doesn't work. In the second example, we're going to find the equivalent resistance seen from the source. In other words, we have 3 resistors. If I want the current flowing out of the source to be the same, and I'm required to get rid of all these resistors, what resistor would I have to choose to get the same current? The first thing I notice about this circuit is that the 9 ohm resistor is actually in parallel with the 6 ohm resistor. It's not easy to see because they're not drawn right next to one another. My first instinct when I see a circuit like this is to draw it in a way where things are more obvious. What really counts in a circuit is not where the components are drawn, but where they're connected. And in this circuit, the 9 ohm resistor is connected to the 6 ohm resistor. You see, it's connected by this wire. This is the same point in the circuit. The other sides of the resistors are connected too by this wire. It's now obvious that the 6 ohm and 9 ohm resistors are in parallel. Let's use the trick we discovered in the last example to combine them. I need to multiply in the numerator and add in the denominator. 9 times 6 is 54. 9 plus 6 is 15. That's 3.6 ohms. I can now see that the 3 ohm resistor is in series with the 3.6 ohm resistor. They lie along the same circuit. 3 plus 3.6 is 6.6 ohms. So I can conclude that the equivalent resistance here is 6.6 ohms. I want to look at a more challenging example next. In this example, we have 5 different resistors that I'd like to combine. My goal here is the same. I'd like to find a single resistor that can substitute for all of them such that the voltage and current through them would be the same. If I start looking at this circuit, though, I'm going to realize very quickly that I have a big problem. None of the resistors are in series, and none of the resistors are in parallel. You might first think that, well, perhaps I'm just not drawing the circuit correctly. If I redrew it, I might be able to discover that some of the resistors are actually in series or in parallel. Let's try. I've redrawn the circuit. It's the same circuit because all the connections are the same, but have I really learned anything more? Is the 2 ohm resistor in parallel with the 4 ohm resistor? Well, no. It would be if the circuit hypothetically looked like this, but that's not what the circuit looks like. We have an 8 ohm resistor here in the middle. What we can learn from this particular configuration of resistors is that using the two methods that we looked at in the previous video, that is, combining resistors in series and in parallel, is not enough in order to combine an arbitrary configuration of resistors. If you need to actually find the equivalent resistor, sometimes you're not going to just be able to combine resistors in series or in parallel. You need more powerful methods in order to actually accomplish the task. We'll get to those in a future video. For this particular example, though, it's actually solvable using a trick. In the future, we'll solve the same problem in a more rigorous way, but let me show you the trick in this particular case. Let's imagine that I have a 12-volt source, and I connect it up to just part of the circuit. Part of the 12 volts will show up across the 2 ohm resistor, and part of the 12 volts will appear across the 4 ohm resistor. Let's find out what fraction of 12 will show up across the 2 ohm resistor and what fraction of 12 will show up across the 4 ohm resistor. We can determine that by finding the current and applying Ohm's law. I equals V over R, and we have 12 volts across the circuit, and our total resistance is 2 plus 4. Therefore, the current flowing through this particular circuit is 2 amperes. If we now apply Ohm's law to each of these two resistors, we can conclude that 8 volts shows up across the 4 ohm resistor because 2 times 4 is 8, and 4 volts shows up across the 2 ohm resistor. Let's now imagine that I have a second 12 volt source, and I put it over here, and I hook it up to the other half of the circuit. I'm now going to follow the same procedure and find out what fraction of the 12 volts appears across the 4 ohm resistor and what fraction of the 12 volts shows up across the 8 ohm resistor. We can find the current through this path by applying Ohm's law. We have 12 volts and a total of 12 ohms, so the current flowing here is just 1 ampere. We can then conclude that 8 volts appears across the 8 ohm resistor and 4 volts appears across the 4 ohm resistor. If we now compare the two circuits that I've just drawn and we look at the voltages appearing across the resistors at the top, we see that they're both 4 volts. Likewise, for the resistors at the bottom, we can see that they're both 8 volts. If I were to connect these two circuits with one another, no current would flow because the voltage drops are the same. For example, if I draw a line right here, no current is going to flow along that line. I could do the same thing here, and I could do the same thing here. No current flows because the voltages are exactly the same. Current can only flow when you have a voltage difference. Let's take this middle line and replace it with a resistor. I could call it R because the same argument holds. It doesn't matter what R is, no current's going to flow through it because the voltage across it is 0. It could be 8 ohms, for instance. Given my set of connections, you might notice that the 12 volt source on the left is just in parallel with the 12 volt source on the right. We only really need one of these sources. We don't need both of them. Let's erase one of them because it applies 12 volts to both sides of the circuit. In order to make the flow of currents clear, I'm going to relabel this current I1 and this current I2. And we know that the 12 volt source on the left is now supplying both of these currents. I1 plus I2 is 3 amperes. The question is now, what equivalent resistor allows that current flowing out of the 12 volt source to be 3 amperes? From Ohm's law, we know it should be 12 divided by I1 plus I2. The correct answer in this case is 4 ohms, but as you can see, the argument is somehow not very satisfying. In a future video, I'll show a more rigorous way of working this type of problem. If you enjoyed watching this video, then you might be interested in following our playlist and learning more about the fundamentals of electrical circuits.